Welcome to the Particle Physics Podcast. In this captivating episode, we invite you on a journey through one of the most ambitious and exciting scientific projects of the 21st century, the Circular Electron-Positron Collider, CEPC, China's next leap in particle physics. What if we could build a machine so precise, so clean, and so powerful that it could decode the nature of the Higgs boson, test the boundaries of the Standard Model, and reveal physics beyond our current theories? In this episode, we shine a spotlight on the Circular Electron-Positron Collider, CEPC, a state-of-the-art electron-positron collider proposed by the Chinese high-energy physics community. Set to span a colossal 100-kilometer underground tunnel, this project could redefine the future of precision particle physics. What is the CEPC, and why is it the world's leading proposal for a Higgs factory? How does it achieve unprecedented measurement precision in a clean lepton collider environment? What are the physics goals across energy stages, Z-pole, WW threshold, Higgs factory, and top threshold? How does CEPC compare with other global projects like CERN's FCCE or Japan's ILC? What is the roadmap toward the Super Proton-Proton Collider, SPPC, a 100 TeV Hadron Collider that may follow? With broad international collaboration already underway, the CEPC is more than a machine. It's a global scientific endeavor. It aims to produce 4 million Higgs bosons, over 3 trillion Z bosons, hundreds of millions of W pairs and top quarks in the upgrade phase. In this deep dive episode, we explore the motivation for a Higgs factory in the post-LHC era, CEPC's staged operation, delivering physics at multiple energy frontiers, the cutting-edge detector technologies and accelerator R&D fueling the project CEPC's global framework of cooperation, governance, and technical exchange, the societal impacts, including talent development, STEM education, and industrial innovation. From subatomic precision to massive infrastructure, the CEPC represents a bold vision to unravel the deepest mysteries of the cosmos, from the nature of mass to potential dark matter interactions, and maybe even hints of new physics waiting to be discovered. This isn't just another collider. It's a scientific milestone, a diplomatic platform, and a legacy-building tool for the next generation of physicists, engineers, and innovators. Don't forget to like, subscribe, and leave a comment. What excites you most about the CEPC? Do you think global collaboration can drive the future of fundamental science? Let's explore the frontiers of particle physics together. Today on the show, we're diving into the world of economic indicators. These are the numbers that tell us how the economy is doing. Things like GDP, unemployment rates, and consumer confidence. But what do these indicators really mean? How are they calculated? And how should we interpret them? We'll break it all down for you, with the help of some experts, to make sense of the numbers that shape our world.
Imagine building a machine so vast it could redefine our understanding of reality. A project so ambitious it aims to train generations of scientists. Or picture this, colliding particles with more energy and, well, at a higher rate than ever before achieved. Sounds like science fiction, right?
It really does.
Well, let's unpack this because we're plunging into the very real and incredibly exciting plans for the Chinese Circular Electron-Positron Collider, or CEPC.
Exactly. And we have, a wealth of technical details here really outlining this colossal undertaking. Our goal today is to move beyond just the impressive specs.
Right.
And truly understand the ingenious design, the groundbreaking technologies being developed, and, well, what this all signifies for the future of how we explore the fundamental building blocks of the universe.
Yeah, our mission isn't just to reel off a list of mind-boggling numbers, is it?
Not at all.
We want to get to the heart of the matter. The core innovations and the immense engineering hurdles involved in constructing a collider of this magnitude. And crucially, what doors this could open in the realm of particle physics.
Think of it as getting a a behind-the-scenes look at the ultimate particle physics laboratory of tomorrow.
All right, so let's get straight to the core ambition then. What is the CEPC ultimately trying to achieve in terms of its performance?
Okay. The CEPC is fundamentally about pushing the frontiers of two key aspects. Beam energy, which lets us probe deeper into the structure of matter, and luminosity. Now, luminosity is all about the collision rate. The more collisions we have, the more data we can gather, and, the rarer the phenomena we can observe.
Makes sense.
The CEPC is designed to smash through the performance barrier set by previous giants like LEP2 at CERN and SuperKKB in Japan. And what's particularly exciting, I think, is that the current design already incorporates significant potential for future upgrades.
Upgrades already planned in.
Yeah, meaning its scientific impact could grow even further down the line.
That upgrade potential sounds like built-in future-proofing for discovery. So, okay, give us some of the headline figures that really illustrate the sheer scale and power we're talking about here.
All right. Let's consider the key operating modes. For precision studies of the Higgs boson, the CEPC will operate at a center of mass energy of 120 GeV.
Okay.
But it's also designed to delve into the worlds of other fundamental particles, with operation around 45.5 GeV for Z bosons, 80 GeV for W bosons, and 180 GeV for top quarks also planned.
A real particle factory.
Pretty much. Now prepare yourself for this. The main collider ring will have a circumference of approximately 100 kilometers.
100 kilometers. Just let that sink in for a moment. The Large Hadron Collider, which already feels enormous, is what, 27 kilometers?
That's right.
This is on a completely different scale. What does that immense size buy us?
Well, that massive circumference allows for more powerful acceleration of the particles, and crucially, helps to manage the immense energy they lose as they travel in a circle. That phenomenon called synchrotron radiation. This ring will initially host two interaction points where the meticulously prepared beams of electrons and positrons will collide head-on. And the power of the synchrotron radiation emitted by these beams, especially with future upgrades, could reach an astounding 50 megawatts per beam.
50 megawatts. Wow, that's an incredible amount of energy just being radiated away.
It is.
It really highlights the power we're dealing with and the engineering challenge of managing it. Now, let's talk about those collisions you mentioned, luminosity. What kind of collision rates are we expecting?
So the luminosity targets are truly ambitious. For Higgs studies, the goal is around 5.0 times 10 to the 34 per square centimeter per second per interaction point.
Okay, 5 times 10 to the 34.
But for producing Z bosons, the CEPC is aiming for an incredible 115 times 10 to the 34.
Oh, 115.
Yeah. To put that in perspective, that's an absolutely staggering number of potential interactions happening every single second.
Those numbers are almost incomprehensible in their magnitude. How do they even begin to manage that many particles in collision?
Well, the particle beams themselves are structured into numerous packets or bunches, of electrons and positrons.
What's it?
The number of these bunches and the spacing between them will be carefully controlled depending on the specific energy we want to achieve. For instance, when studying the Higgs, we might have around, say, 446 bunches separated by about 355 nanoseconds, including a significant gap to manage the beam. But when we shift to producing Z bosons, the number of bunches skyrockets to over 13,000 with a much tighter spacing of just 23 nanoseconds.
13,000 bunches.
Yep. And naturally, the total current in the beam will also increase dramatically in these high luminosity modes, potentially reaching over 1.3 amps in Z mode.
So we're talking about tens of thousands of tightly packed particle bunches racing around this gigantic ring at near the speed of light. What keeps these incredibly dense beams focused and ensures they collide at the right place and time?
That's the job of a meticulously designed system of magnetic fields. You have parameters like beta functions at the interaction points, measured in meters and even millimeters.
Okay.
And the emittance of the beam, measured in incredibly small units like nanometers and picometers. These dictate the size and spread of the beam.
Beta functions and emittance. Got it.
Think of beta functions as a measure of how tightly we can squeeze the beam at the collision point. The smaller the beta function, the tighter the focus. For the Higgs mode, we're talking about a horizontal focus down to just 0.3 meters and a vertical focus of a mere 1 millimeter.
1 millimeter vertically.
1 millimeter. Achieving such a tight focus for beams traveling across a 100-kilometer ring with such precision is, well, an extraordinary feat of engineering.
Millimeter scale focusing across that distance. The sheer precision required is just mind-blowing.
It truly is. And then we have to consider the lifespan of these beams, phenomena like Baupau scattering, where electrons and positrons scatter off each other.
Right.
And beam Strahling, that's synchrotron radiation, emitted due to the intense electromagnetic fields within the colliding punches, they gradually deplete the beams.
So the beams don't last forever?
No. For example, the estimated beam lifetime in Higgs mode due to these effects is around 40 minutes.
40 minutes. Okay.
While that might not sound long, maintaining such intense beams for that duration in a machine of this scale is, frankly, a testament to the sophistication of the design.
You also mentioned this intriguing crab waist collision scheme. What's the clever idea behind that?
Ah, yes. To achieve those extremely high luminosities, the CEPC plans to use a very sophisticated technique called the crab waist collision scheme, combined with a large Powinsky angle.
Crab waist, Polinski angle. Okay.
Imagine the two colliding bunches not as simple points, but as elongated thin ribbons. The crab waist scheme essentially rotates or tilts these ribbons ever so slightly just before they collide.
Tilts them. How does that help?
Well, this maximizes the area of overlap during the collision, dramatically increasing the probability of interactions without excessively disrupting the beams. The large Powinsky angle, which relates to the bunch length and the beam size at the collision point, further helps to suppress harmful beam effects that can arise with such intense collisions.
Okay.
But the core insight here is to move beyond a simple head-on smash and instead orchestrate a more glancing but much more effective interaction.
So it's kind of like angling two streams of water just right to create a much larger splash zone.
That's a pretty good analogy, actually.
A really ingenious way to boost the collision rate.
Exactly. However, operating at these unprecedented parameters also introduces new physics challenges. We have to contend with significant beam Strahlung, that intense synchrotron radiation generated by the colliding beams themselves.
Right, you mentioned that.
And there's also the coherent XZ instability, which is a novel type of beam instability that can become significant with the large crossing angles inherent in the crab waist scheme.
So new challenges pop up too.
Absolutely. So while we're pushing the boundaries of discovery, we're also venturing into, well, uncharted territory in terms of beam physics.
It sounds like they're not just building a bigger collider. They're innovating in fundamental ways to make it work at this scale. Now, let's dive into the actual hardware that will make all of this a reality. What are some of the key subsystems and technologies that are central to the CEPC? Maybe we can start with the magnets, the workhorses of any particle accelerator.
Absolutely. Good place to start. The CEPC will require an enormous and diverse collection of magnets to guide, focus, and precisely shape the particle beams as they hurtle around the 100-kilometer ring.
Okay.
This includes dipole magnets, which are the main bending magnets that keep the particles on the circular track.
Right, the big ones.
Quadrupole magnets, which act like lenses to focus the beam. Sextiopole magnets, which correct for certain imperfections in the focusing. And smaller corrector magnets used for fine-tuning the beam's trajectory.
And just thinking about the sheer number of these magnets, keeping them all aligned with incredible precision across that massive ring, that must be an absolutely colossal undertaking.
It is indeed. The tolerances for misalignment are extraordinarily tight. For the dipole, quadrupole, and sextupole magnets in the main collider ring, the acceptable RMS, that's square errors in their physical position, are on the order of just 100 micrometers.
100 micrometers, that's about the width of a human hair.
Exactly. The angular misalignment must be within 100 microradians. And the magnetic field accuracy itself is also crucial, with field error requirements as low as 0.01% for the dipoles and 0.02% for the quadrupoles and sextupoles.
Wow.
Achieving and maintaining this level of accuracy over such a vast distance is one of the major engineering challenges of the project.
How on earth do they even ensure that level of pinpoint accuracy across such a huge structure?
Well, they will employ a very sophisticated and constantly active correction system. This involves an array of beam position monitors, or BPMs,
BPMs, right.
strategically placed around the ring to precisely measure the beam's position. This information is then fed back to an equally distributed network of corrector magnets.
So it's constantly measuring and adjusting.
Constantly. In each section, or cell, of the collider lattice, there will be 2 BPMs and a set of horizontal and vertical corrector magnets. Furthermore, the sexpole magnets themselves will often incorporate trim coils that allow them to function as additional correctors.
Ah, clever.
And they use techniques like closed-orbit distortion steady correction, which refines the overall path of the beam, dispersion correction, which manages the relationship between the beam's energy and its trajectory, and beta beating correction, which ensures the focusing properties of the magnets are as designed. These are applied iteratively throughout the machine's operation.
So it's a continuous process of measurement, adjustment, like a super precise self-regulating system.
Exactly. It's not a one-time alignment. It's a dynamic system that constantly monitors and corrects for even the slightest deviations.
What about the magnets themselves? Are there any particularly innovative designs being used in the CEPC?
Yes, particularly in the booster ring. Now, the booster is a smaller accelerator ring that takes the initial 30 GeV electron and positron beams from the linear accelerator
Okay, the pre-accelerator.
and further accelerates them up to 80 GeV before they are injected into the main 100-kilometer collider ring. The booster will utilize twin aperture magnets for its dipole bending magnets.
Twin aperture, what does that mean?
It means that within a single magnetic structure, there are two separate beam pipes, each guiding one of the beam's electrons in one, positrons in the other.
Oh, I see.
These magnets are designed with a DT4 iron yoke and a common air-cooled coil, which can lead to savings in space and potentially in cost. It's like getting two magnets in one package, really.
That sounds incredibly efficient for the booster stage. And how do they ensure the quality and performance of such a massive number of magnets, both in the booster and the main ring?
Precise magnetic field measurement is absolutely critical. For a project like the CEPC, with literally thousands of magnets, some of which can be up to 6.5 meters in length,
6.5 meters.
accurately and efficiently measuring the characteristics of their magnetic fields is a significant undertaking. To address this, they are developing advanced prototypes of 6.5-meter-long magnetic measurement systems. These systems will employ both rotating coil technology, which is very precise for measuring field integrals and harmonics, and Hall probe technology, which can map the field point by point. These systems will need to precisely determine parameters like the integrated field strength, the central field gradient, the effective magnetic length, the higher-order harmonic components of the field, and the precise location of the magnetic center.
So many parameters to check for each one.
Ensuring the uniformity and accuracy of these magnetic fields is paramount for achieving stable and high-quality beams.
So it's not just about getting the overall strength of the magnetic field, right? It's about the intricate details of its shape and consistency along the entire length of the magnet. And what about the power needed to drive these thousands of magnets? That must be a power grid in itself.
Indeed. The CEPC will require a vast and complex network of power supplies to energize the different types of magnets in both the collider and the booster. The specifications for these power supplies vary dramatically, in terms of their required quantity, their output stability, and their maximum voltage and current ratings.
Give us some examples.
Okay, for example, the collider will have around 44 QAO quadrupole power supplies, each needing to maintain an output stability of 10 parts per million.
10 parts per million.
With a voltage range of 0 to 60 volts. Then you have hundreds of SFI sextupole power supplies with a stability requirement of 20 parts per million and an output capability of up to 200 amps at 110 volts.
Wow.
The booster also has its own specific power supply needs, including ramping DC power supplies that operate at a repetition rate of about 0.045 Hz. For instance, it will need around 16 dipole power supplies capable of delivering 560 amps at 780 volts. The sheer scale and variety is staggering.
And I can only imagine the challenge of keeping them all synchronized and operating with such incredible stability.
Absolutely. To achieve the necessary control precision for these power supplies, the CEPC will be utilizing the second generation of a digital power supply control module, or DPSCM2.
DPSCM2.
This advanced control system was initially developed for the high-energy photon source HEPS project in China.
Oh, okay.
The DPSCM2 uses a powerful field programmable gate array, or FPGA, as its central data processing unit and employs the system on a programmable chip, or SOPC architecture, for the digital control of the power supplies. This allows for highly precise and adaptable control of the magnetic fields.
FPGA-based control, that's some seriously sophisticated power management. Okay, let's move on from the incredible magnet system to another absolutely crucial aspect of any particle accelerator, the vacuum system. We need to create an environment so empty that these particles can travel for vast distances without colliding with air molecules, right?
Precisely. The CEPC will have extraordinarily stringent vacuum requirements, especially in the interaction regions where the electron and positron beams collide within the detectors.
How low are we talking?
In these critical areas, the goal is to achieve a pressure of 3 times 10 to the minus 10 torr, or even lower, specifically outside the first focusing quadrupole magnet.
3 times 10 to the minus 10. That's incredibly low pressure. Many, many times lower than the vacuum we experience in space.
It is. This ultra-high vacuum is absolutely essential to minimize background noise from beam gas scattering, which could obscure the very faint signals of the particle interactions we're trying to observe.
Makes sense. What kind of cutting-edge technology and specialized equipment are required to create and maintain such an extreme vacuum across a 100-kilometer ring?
Well, the vacuum system will be a complex network involving a range of specialized equipment. For the collider's beam pipes, they are planning to use extruded copper chambers that incorporate integrated cooling channels.
Copper. Okay. Why copper?
Copper is an excellent choice here due to its high thermal conductivity and low electrical resistivity. Those cooling channels are absolutely vital for dissipating the significant heat load generated by the synchrotron radiation and also higher order mode losses from the intense particle beams.
Right, the heat load again.
And the fabrication process for these copper chambers is quite involved. Extrusion to create the basic shape, precision welding to join sections, stretch forming to achieve the final dimensions, and brazing to ensure leak-tight connections for the cooling channels.
A lot of steps involved. But with such high energy particles flying around, those vacuum chambers must be bombarded by a lot of radiation. How do they protect the equipment and maintain the integrity of the vacuum?
You're absolutely right. The particle fluence, meaning the number of synchrotron radiation photons and secondary particles hitting the vacuum chambers, will be substantial. They are using sophisticated Monte Carlo simulations to meticulously study this radiation and its potential impact on various components.
Okay.
There will be certain areas of particularly high fluence, for example, in the small gaps between adjacent magnets where traditional lead shielding might not completely cover the beam pipes near the connecting flanges.
Ah, the gaps.
Yeah, this escaping radiation could potentially damage the magnet coils and other sensitive equipment nearby. So the detailed design of these intermagnet regions will be absolutely crucial during the engineering design phase.
Right.
Additionally, in the interaction regions, where beam Strahlen, the intense radiation from the colliding beams, is a major concern, they are considering using beam pipes made from tungsten alloys and adding extra tungsten shielding around the superconducting magnet cryostats to protect the detectors.
So strategic shielding with lead and tungsten. What about the inner surfaces of the vacuum chambers themselves? Do they get any special treatments or coatings?
Yes, they will be applying NEG coatings. NEG stands for non-evaporable getter.
NEG coatings, what do they do?
Materials like Tizar-V, that's titanium, zirconium, vanadium, and Tizar-VHF adding hafnium are being considered. These special coatings have the remarkable ability to absorb residual gas molecules that might be present within the vacuum system, helping to maintain that crucial ultra-high vacuum over long periods.
Like a molecular sponge.
Pretty much. However, there's a delicate balancing act involved here. The thickness of the NAG coating needs to be carefully controlled.
Why is that?
Well, while a thicker coating would generally improve the pumping efficiency and extend the reactivation lifetime of the getter material, these coatings typically have a lower electrical conductivity compared to the copper of the chamber itself.
Ah, okay.
This increased electrical resistance can lead to a higher machine impedance, which can potentially destabilize the particle beams. Current simulations suggest that the average thickness of the NEG coating should likely not exceed around 200 nanometers to maintain acceptable beam dynamics.
It's a really intricate balancing act, needing that coating for the vacuum, but also needing to minimize its impact on the beams themselves.
Whoa.
Now, you've mentioned synchrotron radiation quite a few times. Can you explain a bit more about why it's such a fundamental consideration for the CEPC?
Sure. Synchrotron radiation is an unavoidable consequence of accelerating charged particles, like the electrons and positrons in the CEPC, in a circular path using bending magnets. As these particles are forced to change direction, they lose energy in the form of photons. That's the synchrotron radiation.
Okay.
The characteristics of this radiation, such as the amount of energy lost, the total power emitted, and the energy spectrum of the photons depend directly on the energy of the particle beam and the bending radius of the magnets.
And at CEPC energies.
Well, for example, when the CEPC is operating at the Higgs energy of 120 GeV, each electron and positron will lose an estimated 1.8 GeV of energy with every single turn around the 100-kilometer ring.
1.8 GeV per turn. That's huge.
It is. The total synchrotron radiation power emitted by the entire beam is proportional to the circulating beam current and, crucially, to the fourth power of the beam energy.
The fourth power.
Yes. This is why it becomes such a dominant factor at the high energies envisioned for the CEPC, leading to those massive power figures we discussed earlier, like 50 megawatts per beam, potentially. The critical energy of the synchrotron spectrum gives us an idea of the average energy of the emitted photons. A higher critical energy means more high-energy, harder photons are being produced.
So it's not just a tiny bit of lost energy. It's a significant and continuous drain on the particle's energy, requiring a powerful RF system to replenish it. And it's also a source of intense heat and potentially damaging radiation. How do they manage this immense power output?
Managing the heat load generated by the synchrotron radiation is absolutely critical. This is the primary reason why the copper beam pipes with integrated cooling channels are so important.
Right, the cooling channels.
The cooling water flowing through these channels will continuously remove the heat deposited by the radiation. They rely heavily on detailed Monte Carlo simulations to predict precisely where this radiation will strike the vacuum chambers and how much energy will be deposited.
Simulations are key.
Absolutely. These simulations also help them to calculate the resulting absorbed doses to the insulation materials of the magnets and the overall energy deposition within the magnets themselves and the tunnel structure. As we discussed, areas where the radiation might escape direct shielding, like the gaps between magnets, require particularly careful design to prevent overheating or damage to sensitive components, like the magnet coils and nearby electronics.
It sounds like a constant battle against the fundamental physics, trying to accelerate these particles to incredible energies while constantly fighting against the energy they lose and the radiation they produce. Let's move on to another absolutely vital system, the radio frequency, or RF system. This is the system that provides the energy kick to the particles to compensate for the energy lost through synchrotron radiation and also helps to bunch them together, right?
Exactly. The RF system is the heart of the energy management for the accelerator. It provides the electromagnetic fields that continuously add energy to the particle beams, replacing exactly what they lose through synchrotron radiation. It also plays a crucial role in shaping and synchronizing the bunches of electrons and positrons, ensuring they are tightly packed and arrive at the interaction points at precisely the right moment for collisions.
Where will this system be located?
The CEPC will have dedicated RF sections located in two of its long, straight sections, both for the main collider ring and for the smaller booster ring. The collider will utilize superconducting RF cavities operating at a frequency of 650 megahertz.
650 megahertz for the collider.
While the booster will employ superconducting RF cavities at a higher frequency of 1.3 gigahertz.
Superconducting cavities, that means they need to be cooled down to incredibly low temperatures using that sophisticated cryogenic system we'll discuss later, correct?
That's right. The superconducting materials used in these cavities only exhibit their near-zero electrical resistance at cryogenic temperatures, typically just a few degrees above absolute zero. This allows for very efficient energy transfer to the particle beams.
How will they be housed?
In the collider, these superconducting cavities will be housed in cryomodules, which will be mounted directly on the floor of the tunnel. In the booster ring, the cryomodules will also contain superconducting cavities, but will be suspended from the ceiling of the tunnel at a slightly different beamline height.
Oh, interesting.
Positioned in between the sections of the collider cryomodules. The collider cavities will operate in a continuous wave, or CW mode, constantly providing energy to the beams. In contrast, the booster cavities will use a fast voltage ramp mode, rapidly increasing their accelerating voltage to efficiently boost the energy of the injected beams.
It's interesting that they're using different RF frequencies for the collider and the booster. What's the reason behind that choice?
Well, the selection of the RF frequency is often a complex trade-off. It involves factors like the physical size of the cavities, their electrical impedance, which affects how easily they can transfer energy to the beam, and the desired accelerating gradient, the amount of energy they can impart to the particles per unit length. Higher frequencies generally allow for more compact cavities, which can be beneficial in terms of space constraints, but can also lead to higher impedance. The specific operational requirements of the collider and the booster, like the total energy gain needed per turn and the need for rapid acceleration of the booster, likely dictated these frequency choices.
Makes sense.
Additionally, to optimize the efficiency of the RF system in the collider, they are planning a common cavity scheme for operations at the top quark and Higgs energy levels, both of which require very high RF voltages.
Okay.
Separate sets of cavities will be used for the W and Z boson energy regimes, which require lower RF voltages. This approach can potentially reduce the total number of cavities and associated cryomodules needed, leading to cost and energy savings.
That sounds like a very smart way to tailor the RF system to the specific needs of each operating mode. What about the actual power sources that drive these RF cavities?
The high-voltage power supply for these superconducting RF sources is a critical piece of the puzzle. Traditionally, pulse-step modulation, or PSM power supplies, have been widely used. However, they can sometimes have limitations, particularly in terms of the level of high-voltage ripple they produce and their long-term output stability. Given the demanding requirements of the CEPC for beam quality and stability, very stable RF power will be essential.
So they might be looking at more advanced or alternative power supply technologies?
Potentially, the documentation notes that the typical performance of commercially available PSM power supplies currently yields a voltage ripple and long-term stability around 1%, which might not be optimal for the CEPC's goals.
Okay.
The field of power electronics is constantly evolving, so it's possible that more stable and energy-efficient power supply solutions will be adopted as the project progresses. For the injector LINAC, which operates at S-band, around 2.86 GHz, and C-band, around 5.7 GHz frequencies, powerful klystron tubes will be used as the primary power sources,
Klystrons, right.
capable of generating very high accelerating gradients. For the damping ring, which operates at a lower energy, they are considering using normal conducting 5-cell RF cavities operating at 650 MHz. They're also exploring the potential of using solid-state amplifiers, or SSAs, as power sources for the damping ring RF system.
SSAs.
Yes, solid-state amplifiers. They offer advantages like high efficiency and potentially greater reliability compared to tube-based systems.
Klystrons, normal conducting cavities, solid-state amplifiers. It's a real mix and match of RF technologies, each chosen for the specific demands of its role within the accelerator complex. And all of this incredibly precise RF power needs to be meticulously controlled, right? That's where the low-level RF or LRF system comes into play.
Exactly. The LRF system is essentially the brain of the entire RF system. It's responsible for maintaining the stability of the RF cavities and the power sources by continuously monitoring all the relevant signals, things like the cavity voltage, phase, and frequency, and then making real-time adjustment to the power delivered to the cavities. It also plays a crucial role in synchronizing the RF system with other critical accelerator systems, like the timing systems.
How does it handle the large distances?
Well, for the collider and booster, which each operate at a single fixed RF frequency, a very stable and precise RF transfer system will be essential for distributing the reference signals accurately across the large distances. This system will likely rely on a combination of high-quality coaxial cables and low-loss optical fiber.
Optical fiber, okay.
The injector LINAC, being a long linear structure with particularly stringent requirements for phase stability along its length, will also likely use optical fiber for the precise distribution of its reference RF signals. And for the damping ring, the LLRF system will need to manage the acceleration of two distinct bunches of particles simultaneously, ensuring stable waveforms and likely incorporating feedback and potentially feed-forward control mechanisms to compensate for beam loading effects.
Beam loading. That's where the beam itself affects the RF field.
Exactly. The energy the beam takes out can affect the fields within the RF cavities, so the LORF needs to compensate for that.
It sounds like a LRF system is the conductor of this high-frequency orchestra, making sure every component is playing in perfect harmony. Now, we can't possibly build and operate a machine as complex as the CEPC without incredibly sophisticated instrumentation to constantly monitor and control the particle beams. What kind of instruments will be absolutely crucial for its success?
Oh, a vast array of specialized instrumentation will be essential for every aspect of beam monitoring and control. Beam position measurement, or BPM systems, will be absolutely critical for accurately determining the position of the electron and positron beams as they travel around the entire accelerator complex.
Right, the BPMs again. Very important.
The precise position data from the BPMs is used to calculate a wide range of crucial machine parameters and to actively correct the beam's orbit using the corrector magnets we discussed earlier. Beam current measurement techniques will also be vital to know the intensity or the number of particles in each beam bunch. Synchrotron light-based measurement, where they analyze the properties of the synchrotron radiation emitted by the particles, can provide valuable information about the beam size, shape, and energy distribution.
Using the light the beam emits. Clever.
And a beam loss monitor, or BLM system, will be crucial for detecting any particles that stray from their intended path. This is important not only for protecting the accelerator components from potential damage, but also for identifying and diagnosing any issues with beam stability or guidance.
So the BLMs act like detectors for lost particles.
Essentially, yes. The CEPC booster, for example, will utilize a specialized BLM system based on detecting Cherenkov light generated when lost particles pass through a quartz fiber. Photomultiplier tubes at both ends of the fiber will help to pinpoint the location of these beam losses.
So the BLMs are like the early warning system, immediately alerting operators to any wayward particles. What other essential instrumentation will be in place?
Well, a tune measurement system will be used to precisely measure the betatron tune, which is a fundamental property related to the oscillation frequency of the particles around their ideal orbit.
The tune. Important for stability. Yeah.
Critical for ensuring long-term beam stability. And of course, a sophisticated beam feedback system will be absolutely necessary to dampen any unwanted oscillations or instabilities that can arise in the intense particle beams.
How does that work?
The CEPC will employ a bunch-by-bunch digital feedback system, capable of independently monitoring and correcting the behavior of each individual bunch of particles to suppress coupled bunch instabilities.
Okay.
A typical transverse feedback system includes front-end electronics to process the signals from the BPMs, advanced digital processing electronics to calculate the necessary corrections, like applying phase shifts, a powerful amplifier to boost the correction signal, and a kicker magnet to apply a small, precisely timed angular kick to the beam to counteract the unwanted oscillations.
A kicker magnet to nudge the beam back in line.
Exactly. And for incredibly fine-grained measurements, researchers at BEPC2 have even explored using electrical capacitive displacement detectors with nanometer-level accuracy to directly measure any minute displacements of the BPM vacuum chambers themselves.
Nanometer accuracy in measuring vacuum chamber movement. The level of precision across all these instrumentation systems is truly breathtaking. Now, all of this incredibly complex hardware and instrumentation needs to work together flawlessly. That's where the overarching control system comes in. What will be the architecture of the CEPC's central nervous system?
The overall control system for the CEPC will be a highly complex and distributed architecture, responsible for the seamless monitoring and control of every single aspect of the vast accelerator complex. Pretty much everything, from the thousands of power supplies for the magnets and the operation of the vacuum pumps and valves to the intricate settings of the RF system and the data acquisition from all the various instrumentation systems.
Wow.
For instance, the control system will manage the precise settings and monitor the operational status of all the magnet power supplies. It will oversee the operation of the numerous vacuum pumps and valves. It will integrate the data and control functions for all the other critical subsystems.
What kind of software or frameworks?
The control system for the injector LINAC, for example, will utilize the widely adopted EPCS, that's Experimental Physics and Industrial Control System framework, and the PVA, or PV Access, protocol for efficient communication.
EPCS, okay?
And to ensure smooth and safe operation, and to facilitate rapid troubleshooting, a comprehensive alarm system will be implemented to immediately alert operators to any faults or abnormal conditions.
Alarms are crucial.
Absolutely. Complementing this, a sophisticated post-mortem data storage and analysis system will be crucial. This system will automatically record and archive detailed data from all the key subsystems whenever a fault or unexpected beam behavior occurs.
Ah, like a black box recorder.
Exactly. It allows engineers and physicists to thoroughly analyze the events, diagnose the root causes, and implement measures to prevent future recurrences. Specific subsystems, like the fast injection and extraction kickers in the damping ring, will have their own dedicated control systems. And for managing vacuum valves and monitoring pressure in the damping ring, programmable logic controllers, or PLCs, will be employed.
PLCs for the vacuum.
Yeah. And the RF control system will handle monitoring klystron status, controlling power sources, setting voltage and phase, managing cavity tuning, and interfacing with the interlock system for safety.
So this control system really is the central nervous system, constantly monitoring, adjusting, and ensuring the safety and stability of the beams and all the interconnected equipment across this massive facility. Now, we've talked a lot about the superconducting RF cavities, and we know they require incredibly low temperatures to function. This brings us to the crucial cryogenic system. What can you tell us about how the CEPC will achieve and maintain these frigid temperatures?
Right, the cryogenic system is absolutely indispensable for the operation of the hundreds of superconducting RF cavities in both the booster and the main collider rings.
Hundreds of them.
Yeah. For the high-luminosity Higgs operation mode, the current design calls for 96 1.3 gigahertz cavities in the booster and 336 650 megahertz cavities in the collider. These cavities must be cooled to extremely low temperatures, typically around 2 Kelvin for the 1.3 gigahertz cavities, and around 4.5 Kelvin for the 650 megahertz cavities to get their superconducting properties.
2 Kelvin, that's incredibly cold.
It is, just degrees above absolute zero. To achieve and maintain these temperatures, the cryogenic system will be designed to provide a substantial amount of cooling capacity. For the Higgs 50 milliW operation mode, it's estimated that the total heat load that needs to be removed at 4.5 Kelvin will be around 15 kilowatts for each of the 4 independent cryogenic stations distributed around the ring.
15 kilowatts of cooling at just 4.5 Kelvin. That's a massive amount of refrigeration power. How does this translate into the actual hardware? We're talking about more than just a giant freezer, I imagine.
Oh, absolutely. The cryogenic system will involve a complex network of helium refrigerators, extensive distribution lines to transport the ultra-cold helium, and sophisticated cryostats to house the superconducting components and provide thermal insulation.
Oh,
There's also the potential for strategically splitting the overall cryogenic system into more modular components, like a dedicated 4 Kelvin system, a separate 2 Kelvin heat exchanger unit, and specialized helium decompression machinery. This could potentially enhance the security of the supply chain and reduce technical dependencies.
makes sense from a project management perspective.
One of the key technical challenges here is the development of a high flow rate and highly efficient 2 Kelvin heat exchanger, which is crucial for achieving the required low temperatures for those 1.3 gigahertz booster cavities.
So it's not just about reaching those incredibly low temperatures, it's about doing it efficiently, reliably, and on a massive scale across the entire 100-kilometer infrastructure. Now, the very heart of the CEPC, where the exciting particle collisions actually occur, is the interaction region, or IR. This is where the massive particle detectors will be located. What are some of the unique design considerations and challenges for this critical region?
Right, the interaction region, or IR, and the machine detector interface, or MDI, that crucial zone where the accelerator components meet the detectors, present a unique set of design challenges.
MDI, okay.
The layout of the IR will feature an asymmetric arrangement of focusing magnets and a reverse bending scheme in the final sections leading into the interaction point.
Reverse bending, why?
This clever reverse bending is specifically designed to prevent the intense synchrotron radiation generated upstream from directly hitting the sensitive detector chamber.
Yeah.
You want to keep that background noise down.
Right, protecting the detector.
Exactly. Furthermore, to accommodate a potential future super-proton collider, or SPPC, that could potentially be built in the same tunnel later.
Planning ahead again.
The overall geometry of the IR for the CEPC is being designed with the capability to be retracted relative to the main collider ring. This would allow for smoother bends in the beam line for the SPPC bypass section.
That's some impressive foresight. What about the more immediate engineering challenges within the IR for the CEPC itself?
Well, the MDI is where we encounter significant mechanical design complexities. There's very limited physical space available due to the compact arrangement of the final focusing magnets and the detector itself.
Tight squeeze.
Very tight. At the same time, there are extremely stringent demands for mechanical stability and precise alignment, We're talking about alignment requirements for the superconducting magnets in the MDI that are better than 100 micrometers again.
Micrometer precision in that crowded space.
Yep. Critical components include the remote vacuum connector, or RVC, which allows connecting the vacuum system without disturbing the detector, and the sophisticated support system for the superconducting magnets. These supports will use sturdy pedestals equipped with fine-tuning adjusting mechanisms for movement in all 6 degrees of freedom, allowing incredibly precise alignment.
6 degrees of freedom. Wow.
They've even done optimization studies to determine the ideal number of supports for the heavy dipole magnets to minimize deformation due to gravity. Additionally, specialized collimators will be strategically placed within the IR to intercept and absorb the intense beam-strolling radiation, protecting the delicate detector components.
It sounds like the IR and MDI are incredibly tightly packed and precisely engineered environments where every single millimeter and micrometer truly counts. Now, we've spent a lot of time discussing the main collider ring and the booster, but before the particles even reach those stages, they need to be generated and initially accelerated. This brings us to the crucial LINAC, the damping ring, and the very sources of the electrons and positrons. Can you give us an overview of these vital upstream components?
Sure. The linear accelerator, or LINAC, is the first stage in the acceleration chain. Its primary role is to generate the initial beams of electrons and positrons and accelerate them up to an energy of 30 GeV before they are injected into the booster ring.
30 GeV from the LINAC.
Right. The LINAC itself is a complex system with several key sections. The electron source and bunching system, ESBS, the front-end accelerator section, FAS, the electron beam transport line, EBTL, to the positron target, and the target area section, TAS, where positrons are produced. The LINAC will use powerful klystrons operating at both S-band and C-band frequencies to power its accelerating structures, allowing it to achieve very high accelerating gradients.
How accurate does the LINAC beam need to be?
Very. They've performed detailed error studies. These simulations show that with appropriate correction systems, the beam orbits can be kept within 0.5 millimeters, and the energy jitter and energy spread can be maintained within the strict requirements for efficient injection into the booster.
So the LINAC is like the long runway where the particles get up to their initial takeoff speed of 30 GeV. What happens to these high-energy beams after they exit the LINAC?
After exiting the LINAC at 30 GeV, the beams are injected into the damping ring.
The damping ring, what does that do?
The damping ring is a smaller, specialized storage ring designed to significantly reduce the emittance of the beams. Remember emittance. It's a measure of the spread or disorder of the particles.
Right, making the beam tighter.
Exactly. The damping ring effectively cools down the beams, making them much denser and more suitable for efficient injection into the main collider ring. The CEPC damping ring will operate at 1.1 GeV and have a circumference of about 147 meters. It will use normal conducting RF cavities at 650 MHz.
Normal conducting here, okay.
Yeah. It has its own injection and extraction systems and specialized transport lines connecting it to the LINAC and the booster. These lines further manipulate the beam, like compressing the energy spread before injection and reducing bunch length after extraction. Maintaining low impedance in the damping ring is also critical for stability.
So the damping ring is like a beam conditioning center, taking the somewhat raw beams from the LINAC and refining them into tightly packed, high-quality beams ready for the main acceleration and collision. And where do these initial streams of electrons and positrons actually originate?
The initial source of electrons will likely be a conventional electron gun, which is pretty standard technology. For the positron source, they are considering using a flux concentrator, also known as an adiabatic matching device, or AMD. This uses a very strong pulsed magnetic field to focus the positrons produced when the high-energy electron beam from the LINAC hits a special target.
Focusing the positrons.
Yeah, it significantly increases the number of positrons that can be captured and accelerated. In the transport line carrying the beams between the LINAC, target, and damping ring, S-band RF systems are used to further manipulate beam properties, like energy spread and bunch length.
It's a really intricate and multi-stage process, starting from the fundamental generation of electrons and positrons all the way through to their final collision in the main collider ring. Now, with a project as large and complex as the CEPC, the overall physical layout and the structures that will house it are also incredibly important. What will the CEPC facility actually look like?
Well, the CEPC complex will primarily be an underground facility. The massive collider ring and the booster ring will share the same main tunnel, which, as we know, will be about 100 kilometers around.
Right.
This main tunnel will consist of curved arc sections, the interaction regions, IP1 and IP3 for the detectors, the RS sections, IP2 and IP4, and connecting linear sections. The smaller booster ring and the Linux BTL beam transfer line will have their own dedicated tunnels.
And on the surface?
On the surface, there will be a number of auxiliary buildings for essential equipment: power supplies, cryogenic plants, control rooms, other support infrastructure. The two large experimental halls for the detectors will be deep underground at the interaction points, maybe 80 to 160 meters down. Access will be via vertical shafts around the ring.
100 kilometers of underground tunnels and massive underground experimental halls. That's a civil engineering project of truly epic proportions. And I recall seeing something about a science city being associated with the CEPC project.
Yes, that's right. The concept of a comprehensive science city is being actively developed alongside the CEPC. The idea is to create a vibrant hub for cutting-edge scientific research and technological development centered around the CEPC facility.
What would that involve?
Well, the planning includes dedicated research labs, educational and training centers for future scientists and engineers, maybe even residential areas for the researchers and staff. The vision is to create not just a research facility, but a thriving ecosystem that fosters innovation and collaboration.
It sounds like they're not just building a scientific instrument. They're aiming to build an entire intellectual and scientific community around it. Now, powering a machine of this scale will undoubtedly require a significant and reliable electrical infrastructure. What can you tell us about the electrical engineering aspects?
Yeah, the design of the electrical system needs to handle a very wide range of power requirements and significant overall loads. Most of the power supplies, especially for the LINAC and magnets, will be DC power supplies using efficient switched mode topologies.
Which mode, okay?
The LINAC power supplies will be modular units with digital control for ease of maintenance. The whole complex will be served by several electrical substations, likely largely unmanned, relying on sophisticated supervisory computer control systems with microprocessor-based protection relays and safety devices for reliable power distribution.
So, a highly automated and remotely managed power distribution system. Given the incredibly high energies, radiation protection and robust safety interlock systems are absolutely paramount. What measures will be in place?
Oh, absolutely critical priorities. They have clear workplace classifications and stringent design criteria for radiation safety. The main radiation sources are interactions of the high-energy beams with matter synchrotron radiation and secondary particles.
Right.
Extensive shielding using lead and potentially other materials will be implemented based on detailed calculations to minimize exposure outside designated zones. A comprehensive personnel safety interlock system, or PSIS, will be implemented.
PSIS, what does that include?
Multiple layers of safety. Sophisticated access control to prevent unauthorized entry into hazardous areas, emergency stop buttons to immediately shut down the accelerator, comprehensive visual and audible alarms, mandatory safety checks of all interlock systems before any operation.
Good.
Plus, a continuous workplace monitoring program will measure radiation levels with automatic alarms if levels exceed safe limits. They're also taking measures to mitigate potential release of any short-lived radionuclides produced in the tunnel air.
A comprehensive, multi-layered safety system is absolutely essential and very reassuring to hear about. Now, with such a vast and incredibly precise machine, the initial alignment during construction and the ongoing maintenance of that alignment will be absolutely crucial. How will they achieve and maintain the required levels of accuracy?
Establishing and maintaining a very precise CEPC alignment control network is fundamental. This network will have a hierarchy of control points: primary, backbone, tunnel, all established with high accuracy using advanced surveying techniques. During tunnel construction and component installation, laser trackers will be the primary tool to determine precise 3D positions, referencing the tunnel control network. The alignment process itself happens in 3 phases: initial installation, an overall survey to check for large-scale deviations, and a final, very precise, smooth alignment to get the final tolerances.
Smooth alignment.
Yeah. The overall strategy is to prioritize the relative alignment between adjacent components in the accelerator lattice.
Relative alignment.
Yes, because the accelerator performance is more sensitive to the precise positioning of neighboring elements than to absolute position over the full 100 kilometers. This helps minimize the impact of any larger global drifts or deformations in the structure.
So it's more about ensuring each component is right relative to its immediate neighbors, rather than absolute perfection across the entire ring. That makes a lot of practical sense. Finally, before we get into the timeline and potential impact, the construction of such a massive underground facility in a specific location presents its own challenges. What about the conventional facilities and the site itself?
Right. The chosen site is in a hilly region with relatively hard metamorphic and magmatic rock. Geological studies show no deep regional fractures and low seismic activity. Groundwater conditions are being carefully studied.
What about the rock quality for tunneling?
The rock types encountered are mostly Class 2 and Class 3, meaning good to relatively fair stability. Comprehensive waterproofing measures will be used for the tunnel ceiling. The large underground experimental halls will require specialized excavation and support techniques.
And the surface layout.
The surface facilities will likely use a mix of centralized and decentralized arrangements. Environmental impact assessments have been done, focusing on forest land protection. The region offers good transportation links and living conditions.
How will they dig the tunnel?
Likely a combination of drilling and blasting, and also using tunnel boring machines, or TBMs, especially for longer sections. The project also includes detailed plans for surface electrical systems, large-scale cooling water systems using both CTW and LCW circuits, fire protection in tunnels and halls, and multiple access shafts.
It sounds like a very carefully selected site with detailed plans for the construction challenges. Now, this is clearly a decades-long project with potential for significant international collaboration. How will it be managed, and what's the proposed timeline?
The management structure involved dedicated accelerator, detector, and theory divisions, with IHEP in Beijing as the host lab. An International Advisory Committee, IAC, has been providing guidance since 2015. For the TDR phase, an International Accelerator Review Committee, IARC, was also formed.
And the timeline.
The plan is to complete the Engineering Design Report, EDR phase, by 2025, aim for government approval between 2026 and 2030, start construction around 2027, and begin initial physics operation around 2035.
2035 for first physics. That's still over a decade away.
It is. International collaborations will be crucial. A proposed structure includes an institution committee, IC, as the governing body with representatives from funding agencies, and a council overseeing scientific and administrative matters. There are also big plans for talent recruitment, training, efficient procurement, and cost-effective manufacturing, possibly using a globally distributed model. KPIs will track industrial support and tech breakthroughs.
That's an ambitious but clearly well-structured roadmap. What about the immense financial investment required? Can you give us a general sense?
Well, a detailed construction cost estimate has been developed using a work breakdown structure, or WBS. It covers the collider, booster, LINAC, damping ring, transport lines, common systems, conventional facilities, and contingency.
Okay.
However, it's important to note what this excludes: manpower costs, cost escalation over time, ongoing operational cost after construction, and pre-construction R&D.
Got it. So the number we see is just for the construction itself.
Primarily, yes. The envisioned operational schedule after commissioning includes about 10 years for Higgs physics, then maybe 2 years for Z boson studies, and 1 year for W boson studies. It highlights the long-term commitment.
So a truly significant long-term investment. Finally, one appendix mentions the potential of CEPC to also serve as a very high-brightness gamma-ray source. That sounds like a fascinating potential spin-off.
It is indeed a very exciting prospect. The CEPC, with its high-energy electron beam, could be an exceptionally powerful source of very high-energy gamma rays, especially above 100 keV.
Better than existing sources.
Preliminary analyses suggest its spectral brightness and flux in this range could significantly surpass current sources like HEPS and SSRF. Realizing this would likely need a dedicated ultra-high-energy synchrotron beamline and advanced ultra-hard X-ray focusing lenses.
Would adding that affect the main collider?
Adding a wiggler magnet to enhance gamma-ray production would slightly increase electron energy loss per turn, but this could likely be compensated by minor adjustments to the main bending magnets.
And what could these gamma rays be used for?
Oh, a remarkably wide range of applications. Fundamental studies in photon nuclear physics, nuclear science, astrophysics, cosmology, tests of QED in extreme fields, and even practical uses in life sciences, materials science, and non-destructive analysis of cultural heritage artifacts.
So the CEPC isn't just about smashing particles. It could open entirely new avenues using these incredibly energetic photons. This has been an absolutely fascinating and incredibly detailed deep dive into the ambitious plans for the Chinese Circular Electron Positron Collider. The sheer scale and complexity, 100-kilometer circumference, nanometer precision, groundbreaking collision schemes. It's truly awe-inspiring.
Absolutely. The CEPC represents a monumental leap forward in particle accelerator technology and has the potential to be a cornerstone of international scientific collaboration for decades. The engineering and technological challenges are immense, but the potential for revolutionary discoveries in our fundamental understanding of the universe is, well, equally profound.
So, considering the decades-long potential of the CEPC and its ambitious goals, what fundamental discoveries do you think are most likely to emerge from this cutting-edge facility? How might they fundamentally reshape our understanding of the universe? Or perhaps, thinking about the global collaboration, how might this project serve as an unprecedented model for future international scientific endeavors on such a massive scale? It certainly provides a vast landscape of thought-provoking possibilities.
Indeed. And if you, the listener, want to delve even deeper into the captivating world of particle physics and the intricate details of the CEPC project, we strongly encourage you to explore the wealth of publicly available research papers, technical documentation, and the websites of the collaborating institutions. There's a universe of information out there for the truly curious to explore.